In 2024, researchers built something that should not exist, a piece of wood, optically transparent, that generates its own electrical charge every time it is tapped or pressed. You heard that right. Not solar wood, not painted on circuitry, the wood itself, doing the generating. Let me tell you what that actually means in plain English. For over a century, see-through and power source have lived on opposite ends of material science, and something as ordinary as timber just closed that gap. And that is just the beginning, because the trick that makes it transparent is the exact same trick that makes it generate power, which is not supposed to be possible. If that contradiction just made you sit up a little, hit a quick like and subscribe so you do not miss the next one. By the end of this video, you will understand exactly how a fibrous, water-loving material out-engineered glass at its own game. Wood has never been the material anyone expected to break new ground. Glass has held that role for the better part of a century, particularly in one specific arms race, the search for windows that do more than just let light in. Researchers at institutions from MIT to Fraunhofer in Germany have spent decades chasing what the industry calls energy-active glazing. Glass that generates power, insulates better, or actively manages heat instead of simply existing as a barrier between inside and outside. The ceiling they kept hitting was always the same. Any coating or layer added to glass to make it do something, capture light, generate a charge, block heat, came at the direct cost of the one thing a window is fundamentally for. Photovoltaic glass coatings and electrochromic smart windows both hit this wall. Adding a functional layer to standard glazing has typically cut light transmission by 20 to 30%, and that is before accounting for the cost of the specialized coating equipment required to apply it at any real scale. Here is what most people get wrong about this. They assume the trade-off is a manufacturing problem, something better engineering eventually solves. It is not. It is closer to a physics problem. Think of it like frosting a cake. The frosting can be beautiful, it can add flavor, it can even be functional, but you no longer have a clean view of the cake underneath, and the more frosting you add, the less cake you actually see. Energy-active glass has followed the same law for decades. Every gain in function has come at a direct, measurable cost to transparency, and every attempt to close that gap has required increasingly exotic, increasingly expensive materials. The result was an industry that treated energy-generating glass as a premium, compromised product rather than a real replacement for ordinary windows. Something architects specified for showcase buildings, never for standard construction. Few people covering this space realize just how long that ceiling has held, or how many well-funded programs quietly hit it and stopped. What almost nobody expected was that the material finally threatening to break through this wall would not be a new kind of glass at all. It would be the thing sitting in the lumberyard the whole time, and figuring out why required looking at wood in a way nobody had seriously tried before. In 2024, a research team working out of Nanjing Forestry University published a study with a modest-sounding goal: build a transparent wood material that could also generate electricity through what is known as the Triboelectric effect. Read that again slowly, because the ambition inside that sentence is enormous. They were not trying to improve on existing transparent wood, which had already existed for years as a decorative material. They were trying to give it a job. The wider materials science community had reason to be skeptical. Wood is fibrous, irregular, and moisture sensitive. Three qualities that sit near the bottom of almost any list of ideal properties for precision electronics. Institutions that had spent decades perfecting engineered glass and polymer-based generators had little reason to expect a genuine breakthrough from timber. This is where the consensus broke. They said the same thing about carbon fiber. For years, traditional aerospace metallurgists dismissed woven carbon composite as a novelty material, too unpredictable to trust in a structure meant to fly. We all know how that ended. Carbon fiber now makes up more than half the structural weight of a modern commercial aircraft. What the Nanjing team actually built was not a coating or an add-on. It was a redesign of wood itself, starting at the cellular level. Using a process called delignification, researchers stripped out lignin, the natural polymer that gives wood its color, its rigidity, and its opacity, leaving behind a scaffold of pure cellulose. That scaffold was then infused with a clear resin engineered to match the refractive index of the cellulose closely enough that light passes straight through instead of scattering. Here is the detail that puts everything into perspective. This was not two separate tricks bolted together for convenience. The structural change that makes the wood transparent is the very same change responsible for its electrical behavior. Strip the wood down correctly, and you are not choosing between clarity and function. You are building both from a single material decision. The early skepticism never slowed the work down. If anything, it sharpened the target. Most coverage of transparent materials stops at the visual trick, how clear it looks, how it feels underhand, whether it could pass for glass in a showroom. The part nobody covers is what happens once you look past the surface and start asking what that same structure could be made to do electrically. And what came out of that lab did not just challenge the old assumption that wood has to be opaque. It challenged something far more stubborn. The assumption that transparency and electrical generation could never share the same material at all. Here is the problem with ordinary wood. It is opaque for a very specific structural reason. Light hits its cell walls and its lignin content and scatters in 100 directions before it ever reaches your eye. Picture fog sitting on a window. The window itself has not changed shape, but every ray of light passing through it is getting bounced and redirected until the view on the other side disappears completely. That is, at a microscopic level, exactly what is happening inside a block of natural wood. Clearing that fog required 2 precise moves, not 1. First, delignification. Soaking the wood in a chemical bath that strips away lignin while leaving the cellulose scaffold. The tube-shaped cell walls that once carried water and nutrients through the living tree, fully intact. What is left behind looks almost skeletal. A pale, porous structure riddled with the same microscopic channels the tree used to feed itself. Second, resin infusion. Researchers filled that porous scaffold with a clear polymer resin chosen specifically because its refractive index closely matches that of the cellulose itself. Here's what most people get wrong about this step. They assume the resin is simply filling empty space like grout in tile. It is doing something more precise than that. By matching the way light bends as it passes from cellulose into resin, the fog scattering effect disappears almost entirely because light no longer has a reason to bounce at the boundary between the two materials. The pilot results were striking. Treated samples achieved optical transmittance figures rivaling ordinary glass while retaining the cellular channel structure of the original wood almost perfectly. Think of it like pulling the frost out of frosted glass and replacing it with something that lets light run straight through, without ever changing the glass's underlying shape. That consequence matters more than it first appears. The wood is not being coated or laminated with a transparent skin. Its own internal architecture becomes the light-passing structure. And that architecture, those channels, those cell walls, that microscopic geometry, does not disappear once the wood turns clear. It is still there. It was never removed. It was simply waiting to be used for something else entirely. This is the detail that rarely makes it into the public reporting on transparent wood. Most articles treat the transparency itself as the finished achievement, a curiosity for design magazines, a novelty for high-end furniture. The channel structure left behind after delignification is not a leftover byproduct of the process. It is the exact geometry that makes the next step possible, and without it, everything that follows simply does not happen. Here is the brutal catch. Making wood transparent meant smoothing out its structure and filling every microscopic gap with resin. Triboelectric generators, devices that produce a charge when two surfaces touch and separate, have historically depended on the opposite. Rough, high-friction, irregular surfaces that maximize electron transfer on contact. Smooth the material down for clarity, and by conventional logic, you should be smoothing away the exact property that would let it generate a charge. For the research team, the bigger problem was not whether transparent wood could look like glass. It was whether a material engineered for optical clarity could still perform electrically at all. What if you did not treat those two goals as competing? What if the same channel structure, responsible for transparency, could also be engineered to hold and route electrical charge? That question led directly to the working device. Researchers layered the transparent wood against a counter-surface material to form what is called a transparent wood-based triboelectric nano generator, a TW-TENG for short. Every time the two surfaces made contact and separated, whether from a tap, a press, or a vibration, they generated a measurable electrical charge, captured through electrodes built directly into the wood's surface. The demonstrated results were not subtle. In testing, the device lit up 19 small LED bulbs using nothing but repeated contact and separation. In a second test, researchers used the same setup to transmit a message in Morse code, proving the output was not just present, but controllable and readable. It sounds like it should not work. A material stripped down and resin-filled, specifically to eliminate light scattering irregularities, should be the last place you would look for a strong triboelectric response. That is exactly why it does. The very channel structure, preserved during delignification, gave the surface enough microscopic texture to sustain contact-based charge generation even after the wood turned optically clear. Transparency and power generation were never actually in conflict. They were sharing the same architecture the entire time, and nobody had engineered the material carefully enough to prove it. That proof came from a single lab bench panel, roughly the size of a coaster, wired to a handful of LEDs on a bench. Most people who read about this never get to the part that actually matters, which is that the effect held up under repeated testing rather than fading after a handful of taps. But a working panel and a working product are two very different claims. Turning a lab bench demonstration into something you could actually build a window, a sensor, or a wall panel out of was an entirely different challenge, and it was the challenge the next phase of the research had to answer. A coaster-sized panel lighting up LEDs on a bench is proof of concept. A window wall generating usable power from rain, wind, and foot traffic across an entire building is a coordination problem, and it is a completely different order of difficulty. Here is where the story really begins, because this is the part almost no coverage of the breakthrough actually gets into. The old approach to energy-generating glass was always additive. Take a finished pane, then bolt, spray, or laminate a functional layer on top of it. A photovoltaic coating here, an electrochromic film there. Every one of those add-on layers introduced its own point of failure: adhesion problems, uneven wear, a visible seam between glass and the thing making it functional. The two properties never fully merged. They just sat next to each other, tolerating one another. Transparent wood does not work that way, and that is the detail that puts everything into perspective. Because the electrical behavior comes from the wood's own internal channel structure rather than a bolted-on layer, the energy harvesting function is not applied to the material. It is grown into it, in the same manufacturing step that makes it transparent in the first place. Think of the difference between painting solar cells onto the outside of a window and growing them directly into the glass itself as part of its molecular structure. One is a surface treatment. The other is a redesign of the material from the inside out. That distinction is what allows this research to point toward genuine architectural and product-scale applications rather than remaining a lab curiosity. Self-powered sensors, smart structural panels, wearable and flexible electronics, all mentioned directly by the researchers behind the work as realistic next steps. Related wood-based generator research, including moisture-driven and bend-driven versions built from natural wood, has already demonstrated stable, sustained electrical output over periods stretching well beyond a single lab session, reinforcing that this is a durable material property and not a one-time trick. The single-sentence verdict is this: a material can now be simultaneously structural, transparent, and electrically active without sacrificing any one property to gain the others. Engineers rarely get to explain this part in public reporting because it is less visually exciting than an LED lighting up, but it is the actual reason this breakthrough scales instead of staying a demonstration piece. Nothing about the electrical function depends on scarce or exotic materials. Cellulose, resin, and a conductive layer are things existing manufacturing infrastructure already knows how to work with. But a compelling set of lab figures is not the same as a certified, independently reportable result. That distinction was about to matter. Here is the honest picture. The certified result behind this story is not a building-scale power plant, and it was never claimed to be one. What the published research from the Nanjing Forestry University team actually demonstrated, confirmed through peer review, is a transparent wood panel capable of lighting 19 small LED bulbs through contact alone, while retaining optical transmittance comparable to standard glass. Translate that into human-scale terms, and the honest picture gets more interesting, not less. 19 LEDs from a tap is not enough to run a household appliance. It is more than enough to power a self-contained sensor, a small display, or a low-draw wearable device, the exact category of small electronics that currently depend on disposable batteries or an external power line. The same demonstration that lit those LEDs was also used to transmit a readable message in Morse code, which matters more than it sounds like it should. A readable, controllable signal proves this is not incidental static. It is usable output. Here is the trade-off this story has to hold on to, honestly. This generates power from motion, contact, and pressure. Taps, vibration, physical touch, not passively from ambient daylight the way a solar panel does. A transparent wood window would not on its own sit quietly in the sun and charge a battery. It would need to be tapped, flexed, or vibrated by wind, rain impact, or foot traffic to produce a charge. That is a real limitation, and it is the honest boundary of what has actually been proven so far. If a piece of ordinary lumber generating a controllable electrical signal from nothing but a tap surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. Inside that honest limitation is the actual payoff. A material this common, treated with a process this replicable, closed a gap between transparency and electrical function that decades of glass research never fully closed. That is not a lab curiosity. That is a new category of material behaving exactly the way engineers had assumed for 100 years, that no material like it ever could. This is the part most coverage of wood generates electricity. Headline skips entirely, because the honest trade-off is less shareable than the headline number. But leaving it out would misrepresent what was actually proven, and this channel does not do that. The question that came next was not whether the demonstration was real. It was who else was going to notice, and what an entire industry built around glass was going to do about it. Windows and glazing make up one of the largest surface areas in the entire built environment, and right now, almost all of that surface area does zero energy work. It exists purely as a barrier, a material that turns even a fraction of that surface area into a functional low-power energy source is not a niche upgrade. It is a change to the baseline assumption behind an entire category of construction material. The sectors this touches are specific, not abstract. Construction materials manufacturing, sustainable building certification, and self-powered sensor design all sit directly in this material's path. Adoption in any of them requires the unglamorous work that always follows a lab breakthrough, reaching cost parity with standard glass, proving weatherproofing over years rather than lab sessions, and clearing building code approval processes that are, by design, slow to trust new materials and structural applications. Here is the historical parallel, and it is quantified rather than vague. Photovoltaic solar cells were dismissed for decades as permanently too expensive to matter outside of niche applications like satellites and calculators. Between the early 2000s and the early 2020s, the cost of solar power fell by more than 90%, a collapse almost nobody in the energy industry predicted, while the technology was still confined to laboratories and specialty use cases. Materials that look economically irrelevant in a lab setting have a documented history of becoming commercially unavoidable once manufacturing catches up to the science. The genuine technical advantage here is harder to replicate than a patent, and that is worth sitting with. Standard glass production is energy intensive and produces a material that, at the end of its life, is not biodegradable. Transparent wood starts from a renewable, biodegradable feedstock, and layers function on top of that foundation rather than working against it. That is not a marketing detail. It is a structural advantage baked into the raw material itself, before a single manufacturing decision gets made. The limit that held this back for decades was never political, and it was never about which country could produce it first. It was technical. Nobody had proven that transparency and electrical function could share the same structure. Now that they have, the same underlying instinct, take an ordinary material, redesign it from the inside out, and watch it outperform something engineered for a century, shows up again in a completely different corner of construction. I already covered the story where that exact instinct got applied to concrete, and what that team found is just as hard to believe as this one. That one is worth your time if this changed how you think about what ordinary materials are still capable of. Step back from the lab bench, and the largest implication of this story has nothing to do with LEDs or Morse code. Humans have been using wood as a building material for longer than almost any other technology in human history, and for nearly all of that time, its role has been fixed. Structural, decorative, occasionally symbolic. This research quietly moved wood into a category it has never belonged to before. An active, engineered material capable of doing electrical work, standing in the same conversation as silicon and glass rather than sitting outside it. That shift matters far beyond one lab and one panel of LEDs because it changes what materials scientists even bother looking for next. If you made it this far, you now understand more about how transparent wood actually works than most people who will read a headline about it today and stop there. You understand why the transparency and the electricity are not two separate achievements bolted together, but a single structural decision. Expressed two different ways. You understand the honest limits of what has been proven and why that honesty makes the achievement more credible, not less. Here is what was actually proven, stated plainly. Transparency and electrical generation are not opposing properties that force a material to choose one over the other. A single, carefully engineered cellulose structure, stripped of lignin and infused with a matched resin, can deliver both properties at once, using a renewable, biodegradable feedstock instead of an energy-intensive one. That is not a marginal improvement on existing smart glass. That is a different category of material altogether, built from something that has been sitting in lumber yards the entire time. Every material on this channel starts out looking ordinary right up until someone bothers to look closely enough. Wood was never the exception to that rule. It just took this long for anyone to prove it. If this changed how you think about what an ordinary material like wood is still capable of, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should breakthrough materials like this one be judged primarily on raw power output or on the sustainability of the source material itself? Both sides of that argument are genuinely defensible, and I want to know where you land. I read every single one. See you in the next one.